All right, this is Horner. We're going to look at number 6 through number 11 for the rotational motion AP Physics C review. And you have an ant that has a mass of m. It's clinging to the rim of this flywheel, radius r, and the wheel is rotating clockwise on a horizontal shaft with an angular velocity of omega. As that wheel rotates, the ant revolves around different points. So one of them is 1, then 2, then 3, then 4, and then comes back up to the top. The ant can adhere to the wheel with a force much greater than its own weight. So therefore we know that the ant never really ever can let go and fall off. It will be most difficult to adhere to the wheel as it revolves past which of the 4 points. So we're going to see that right here, if we do a free body diagram for number 1, so this would be for number 1, point number 1, we'd have mg pointing straight down, and then we also have that adhesion force that is pointing straight down. So we're just going to put F here. So there's some sort of force that is pulling it straight down. If you add the two together, you'd end up with that centripetal force. At point number 2, this one's a little bit different. You'll notice it's probably just a little bit below the horizontal. So you've got a force pointing up into the center of that wheel. We'll put a center here also. In fact, let's just use an X for the center. And then we've got the force of gravity, which is pointing straight down. So obviously 1 is greater than 2. If you go over to point 3, you'll notice that straight down is some force mg, and then pointing straight towards this center would be a force that would of adhesion for that little ant, so we're going to call it F. And then for point 4, we have the same thing that we do here, just in the opposite direction. So we've got a force pointing there. Here's our X again here. And then we've got another force of mg pointing down. So the one where the ant is having the most trouble has got to be letter 3, because you have two forces that are equal, almost and opposite. And so therefore, there's got to be a little bit more adhesion force than there is the force of mg for the bug to stay where it is. All the others are much greater forces holding the bug on. So we know that it's most difficult for it at point 3. If we go to number 7, it says, what is the magnitude of the minimum adhesion force necessary for the ant to stay on the flywheel at point 3? I can't talk today. For this one, we've got to do a little bit of math, and we've got to think about kind of what's going on. So for this one, we know that there is some sort of centripetal force pointing in this direction and the force of gravity pointing in that direction. So we're going to say that that overall centripetal force is mv squared over the radius of the wheel, and we also have then the force of gravity. We can use v, which is linear, is equal to r times omega, which is angular. And if we substitute in for v, so we're going to take these two items and we're going to substitute them in here, we're going to end up with m omega squared r plus mg. And now you should see the answer is clear. It's got to be letter E. For number 8, you have a turntable that's initially at rest, and then it does have a constant angular acceleration of alpha. They want to know what is the angular velocity of the turntable after it's made one complete revolution. So one complete revolution would be a change in angle of 2 pi radians. We know that it's initially at rest, so our original angular velocity is 0. We know that it says it wants us to find the final, so we're not sure what that is, and we have an angular acceleration equal to alpha. So we just have to set up an equation now to see what we would get for for omega f. So omega f is equal to omega plus, and then we'd have alpha times time. Now, this equation obviously would not work because we don't have and we don't need time. The other equation that uses time is the change of position is equal to omega ot plus 1/2, alpha t squared. So neither of these equations are ones that you can use. So the only equation that we have left is omega final squared is equal to omega original squared plus 2 times alpha times the change in the position. So let's use this one. We have omega final is equal to, remember we said that this is 0, and then we have 2 times alpha times our change in position, but we said that that is just 2 pi. Now what we can do is go ahead and do the square root of both sides. So final omega is equal to the square root of 2 times 2 is 4, and then that would be alpha times pi, or pi times alpha. Either one is correct, and so our answer for this one is letter C. For number 9, this is our next question, and we have this really weird looking thing here. And what they tell us is this is a very rigid system, so there's no sway or anything, just rotates. And when it rotates, it goes in a counterclockwise fashion. So we know that that would be a positive angular velocity. We have these masses m and we have masses 2m at radii L and 2L, and they tell us that the masses of the support rod and the crossbars are negligible. So we don't worry about the support posts, so we don't worry about this guy, and then these actually don't have any mass either. And so the angular, the moment of inertia for the system here is going to be the sum of the moment of inertias, and you'll notice that because this bar and this bar doesn't have any, it's negligible mass, we really can just treat the particles as point particles. So that'd be just I is equal to mr squared. So at this point, what we're going to do is we need to go through and figure out for the top bar and the bottom bar, what are the moments of inertia? And then it says they want us to find the ratio of the angular momentum of the upper spheres to that of the lower spheres. So let's go ahead and we're going to call this IT for top, and it's equal to mr squared for the first mass, but be careful because they gave it to us as L. So this is ml squared plus the other mass, which is m times the other distance from the center, which is radius, which is now called L, and that's going to be equal to 2 times ml squared. The moment of inertia for the bottom is the same thing. We're going to use m times r squared. So our mass here for the first one is 2 times m, and then we have the quantity 2l squared plus the same thing again for this side, 2m times 2l squared. 2 times 2 is 4, 4 times 2 is 8, so this is going to be equal to 8 times ml plus 8 times ml squared, and so now we're going to have in the end 16 ml squared. And if we want the ratio, notice that this is 2 over 16. These things, our labels just cross off, and that's equal to 1/8. And so our answer is E. For number 10 and number 11, these are together. We have to treat them as two problems, but they both have this figure in common, so we're going to go ahead and do both. You have a 5 kilogram sphere and a 10 kilogram sphere. They're connected by a rod that does have negligible mass. And so they want to know which of the 5 letter points represents the center mass of the sphere rod combination. So normally we know that at the middle of a rod we would have the center mass would be right here, but because this mass is smaller than this one, it's got to be shifted to the left, and so the only possible answer for us that makes sense is letter B. Number 11 says the sphere rod combination can be pivoted about an axis that is perpendicular to the plane of the page. So that means that if I took a rod and I placed it here in the center, this side would go this way, this side would go this way. If I put it here, it's going to rotate around this way. If I put it here, I'm going to have point E coming around. And they want to know through which axis should we use so that the moment of inertia of the sphere rod combination is the greatest? Well, I want the heavier mass going in the circle, and I want the lighter mass sitting still. So if I put that rod right here, so let's just say I have the rod and I put it right here, then this thing's going to circle around this way or the other way, doesn't matter, and I'd have a really large moment of inertia. So it would be letter A. And that is the end of number 6 through number 11.